Hello, hello, everybody. How are y'all today? Hope you are doing good and safe wherever you might be. We're going to get started at 6:03 as other people might trickle in and get rolling for the rest of the workshop. So 6:03, we will get started. All right, everyone just joining. We're going to get started at 6:03. We're just letting everyone get into the room and settled. All right, everyone, it is 6:03. Hello and welcome. We are happy to have you here this Thursday evening on the East Coast. We're here for our second part of a data science for the medical and biomedical sciences workshop series. We're excited to build off of everything we learned on Thursday and advance our data visiting and analysis skills in R. I am Ann Brown. Nice to meet you all. And Daniel Chen is here to continue leading you through the workshop. We're going to do a quick review of everything. So the first thing I want to make sure to remind everybody is to please go to your video screen, find Daniel Chen, and go to the three-button menu button on the video, and then pin the video of Daniel Chen. So it will stay up in your Zoom window for the entire time. We're not doing a standard screen share so that we can take advantage of seeing both the live coding, Daniel actually talking to us, and the transcript of the entire workshop as well. So please pin Dan's video. I want to remind everyone and thank everyone as well. We are doing this workshop series as part of a pedagogical research study that we are designing, and as a part of Daniel's dissertation. We have two surveys. Some of you might have already taken the pre-workshop survey. If you have not already, please, if you're so inclined to take it, please do. We love survey data. And then at the end of today, we'll also be sending out a link to a post-workshop survey. This is all part of the IRB approved study that we're working on to see how well we can create materials to best meet the needs of our learners. We really welcome this for content and feedback as well. So if anyone doesn't remember me from Tuesday, hi, I'm Dr. Brown. I'm assistant professor here at Virginia Tech, and our leader of this workshop is Daniel Chen, who is such an influence on the carpentries and data education. So I'm glad he's here to lead us through this. I think we have all the links, and I'll be posting links in the chat. The other thing to remember, if you have any questions, post it in the chat to everyone, or you are more than welcome to send me a direct message and I will help you through any issues. I'll be keeping up with the chat and making sure that we have everything taken account and making sure everyone's voice is heard. I'll be posting links as well, so they're easy to get to. All our materials are going to be open access. And then the final thing is we will be sending out one final email tomorrow with links to everything and a final summary if you have any feedback for us. With that, I'm going to turn it over to Dan to get started, and we'll get into the next stage of R.
Okay, hello everyone. As another reminder, make sure that you can currently see the Zoom window and also your RStudio session at the same time. It's going to be essentially more of the same as Tuesday. And just as a slow or sort of a review of what happened on Tuesday and what we're planning on for today. Tuesday, we really just covered the basics of like when you are putting together a data set, how do you want to think about manually entering that data? And that also means that when you see another data set that you've never seen before, how you can identify what might be a problematic from that data set. And that leads us into today in the first portion of cleaning data, where we'll start tackling those very common problems that you would see in a data set that either you curated yourself or you got from someone else. And so just as a really small recap for the next 3 minutes, here's the little exercise for us to work on. And when you're done, you can click the green checkbox on Zoom to say that you're either done with the exercise or you don't want to do the exercise. You're just ready for us to move on. So first, make sure that we have the RStudio project open from Tuesday. Next, load up the two libraries, tidyverse and readxl. The first task from after that, we want to load up the medical data tumor growth Excel sheet and save it to a variable called tumor using the read_Excel function. Once we have the tumor data set loaded up into R, we want to filter the tumor data set such that it only contains values from day 21. And I picked day 21 because it is the last day in this data set where all the groups have a value for. And then we want to calculate the average size for each value of group. And so on the right hand side here, you have sort of a skeleton of the code that I'm asking you to go through. So hopefully this helps jog your memory about how we can use these functions. And so when you're done or you're ready to move on, just use the green checkbox checkmark in Zoom if you can. Or if you need help with something, you can ask the question in chat or put a red X and we'll sort of try to help you there. Okay, so let's slowly go through all the steps in the exercise. So the first part was asking us to make sure that we have the ARP Studio project open. If you're coming in from everything set up on Tuesday, when you open up our studio, you can click the top right corner and navigate to the project that we worked on before. Depending on how you set up, maybe when you open up RStudio, the top right corner already has the RStudio project open for you. So the next thing we want to do is we want to be able to type some code into our computer and have R run it. So we're going to go to the top left corner, go to File, New File. So we have a little place where we can type our code. And the first step was to load up the relevant libraries that we need. So we're going to use tidyverse to make sure that we can work with our data. And then we're going to use the read Excel library to load up an Excel sheet. And just as a reminder, if you have the line of code selected or multiple lines selected, you can hit, I believe it's Control Enter. It's at least Control Enter on a Windows machine to run that code that you have selected. So the next step was to take the tumor growth dataset using the read Excel function. So we can say read underscore Excel. And to navigate to the tumor dataset, it's under the data folder, and then it is the medical data underscore tumor growth. File. So the way we navigate here is we're going to say in quotes, we're going to say data in the data folder, and then we can always hit the tab key to help us navigate our folder system, and then select the medical data underscore tumor growth dot XLSX. And using the tab key is really common when you're working with a programming language because it's trying to help you avoid typos. And once we have this, the next part was to assign this to the variable tumor. So we can say tumor and a little arrow for gets. And now we have this tumor data set that if we simply look at the variable tumor, you can see that it prints out a little the first 10 lines of our data set. And then on the right hand panel in the environment tab, you see that the tumor data is now loaded up. And if we want to look at the entire data set, we can click on the word tumor and it'll pop up that way for us. So the next part was to take the tumor data and then filter the data such that it's values from day 21. So we can use this pipe operator, so tumor, then filter such that the variable day, so it is case sensitive, so it is capital D for in day because the variable itself has a capital letter in it, is equal to 21. So remember, this double equal is the programming way of testing for equality because a single equal is assigning a value just like the arrow symbol that we used earlier. So then we're going to type our little pipe symbol, which is % greater than %. And we pronounce that as then. And we want to calculate the average size for each value of group. So whenever you are trying to think of a problem and you're trying to say, I want to do this one calculation, but it's for like each value of this other variable, that is when we use group by. So we're grouping by the variable group. Then we are running summarize because we're trying to calculate the mean. So the mean is a summary function. When we calculate the mean, we're going to give it a column name called AVG, because that sort of is a variable or column name that would make sense. And then we are telling R to use the mean function around the variable size with the capital letter S to calculate the average size of each tumor across each group. So that is sort of a review from last time. The group by is a very powerful variable, and we can use group by for other variables, multiple variables at the same time. So if we take a look here, we can see there's a group variable and a day variable and an ID. So we could theoretically, filter based off of day. If you have multiple variables that you want to group by, like for each value of group and each value of day, calculate the average size, you can do that as well. In our case, there's only one day for each group, so that calculation won't make sense in this context. But if you have multiple groups that you want, just like using select, you can put a comma and then select the next variable, right? So if you're trying to say for each group and each month, if this was a multi-day study, you want the average tumor across each month in each group, you can as well. All right, so I'm going to save this file as 03-review, just so we have access to this. And then at the end, when we get the big summary email of the YouTube links from the recordings, I'll give you the link to the GitHub page where all of the code that I have typed the last 2 days will be. So if you want another reference of exactly what I typed in class, you have access to that as well. All right, so the next topic we want to go over is really the first main topic of processing and cleaning data. And if you took the survey, one of the questions sort of asked you, like, do you know what tidy data means? Or do you know what wide and long data? And it's sort of a question mark, a question trying to address, like, do you understand that data comes in various shapes? And those are more or less the technical term for talking about the shapes of data. And so tidy data is a concept that really is the first step in data wrangling or data processing. And the concept of tidy data comes from this paper by Hadley Wickham, which I will paste into chat. And it is this paper in the Journal of Statistical Software called Tidy Data. It was written in about 2014, and we're essentially going to go through this paper and code along in R how we can process our data using this paper as a reference. And so in this paper, Hadley talks about data coming in different formats. And the main way we input data is we have this notion of a row and a notion of a column. Right, so here's an example data set. We have 3 patients, each with a hypothetical treatment A and treatment B, and then we have some value between treatments. And if you were putting together your own data set, this is probably something that you would do, is input your data in this format. But in the paper, they talk about the concept that rows and columns in this case are pretty ambiguous, because if all we did was flip the rows and columns such that we have this form of our data, it's exactly the same bits of information. And so, we have all of our patients now in columns, and then for each row represent a treatment. So we could still say, like, what is the difference between all of our patient values, right? So we can take the difference across each column versus before. If we wanted to do that, we would have to operate row-wise, right? So we can create another column that is like column B minus column A, and then we get the delta between the 2 columns. And then in this case, we would really essentially calculate like a row underneath to calculate the delta. And then we'll have another row that's representing the difference between column B and column A, right? And when you're inputting data in Excel, like this is sort of like the pitfalls that you'll run into, because running these calculations gets super tempting to say like, oh, I want to do like cell, what would this be? Like cell B2 minus B1, and then drag the arrow or the cell across, and then we get our difference between our data set, right? And so remember back in the first day where I talked about, don't treat your data set as a visualization, because spreadsheets are really good for manual data entry, and it gets super tempting to be like, oh, I just want to quickly look at this. And then you start doing things to your Excel sheet or your spreadsheet, which is really your raw data, that's actually trying to do like more data analysis work, when you're really trying to keep like a clean spreadsheet for your raw data set. And then Hadley goes on and says that, okay, so those are two versions of that same format of data, but then here's a third one. In this case, we have 3 columns. The first column is the patient's name. The second column is a treatment type. And then the third column is the result. And he goes to argue that this is the format that is quote unquote tidy or clean from an analysis point of view, even though it essentially takes up more space, right? So you as the user who is trying to input this data manually, if we go back to the previous example, it's harder for you to eyeball like which one is doing better or which value is missing from a patient, for example. But this is the value that is more useful if we want to try to do our analysis on a computer. And the one way I can sort of reiterate that point is we just talked about selecting, filtering, group by operations. So I can now actually say group by name and then give me the average result. And it gives me the average treatment result for each person. Or I can say group by treatment and then give me the average result, and then it'll give me the average by treatment, right? And if you're thinking a little bit longer term, like how would I go fit a statistical model? Well, then you can say like, I want the treatment group to predict on what the result would be, right? So now you can literally point to a column, and then that column is a variable in your model, and then the result is another column that is the outcome of interest, right? So even though that this is more of a format that's harder for you as a human to quickly decipher, this is the format of data that is what a lot of these statistical programs want as input. And so in the concept of tidy data, in the third version of the table that's more text, how do we define what is a row and what is a column? Well, so each column should represent a variable. So before we had a variable called person, a variable called treatment, a variable called result, versus before each column was either a separate name or a separate treatment. That's not really a variable, it is a value of a variable. So columns represent variables, rows represent observations. So when we look across a row, it is a single observation of data. And then just like what I mentioned in the first day, make sure that each cell really only has one unit of information in it, right? So we don't want a color associated with this value. We don't want the actual like temperature unit or like the unit in there either, because that's giving us 2 bits of information per cell. And so the benefit of talking about tidy data in this sense is because once you understand this concept of like, I know the outcome, like tidy data and all of this stuff that we're going through is really like the target that you're going to aim for when you are given a brand new piece of data and you need to clean it, right? So it gives you a standardized set of tools and a standardized like outcome to work with, and then all the stuff in the middle are, things that you are going to be super data dependent, or it's going to relate to how your data is stored. But at the end of the day, the goal is to have all of our data sets in the same format. And once we have our data sets all in the same format, then that is a data set that can be easily transferred across different use cases. And so the main common problem that we have is data comes from all of these different inputs and types. And one data, like the first two tables I showed you from Hadley's paper, those are data sets that are really easy and convenient for data entry, but it becomes a problem when you want to do the analysis for it. And so once we have a common set of terminology and a common way to transform data, it makes your data pipeline much smoother, and you can share your data with other people. And so this also goes back into the first day where I'm saying it doesn't matter that first point or second point where we talked about, as long as you have a plan for how you're going to work with your data set, it's not going to be that messy. And so even if you input your data in a format that's convenient because it's less error prone for your data entry, think about how you might be able to transform that can be used later on. And so the first example in this paper, so now we're going back to Hadley's paper. The first example he goes through is this example of different religions and their income bracket and how many people responded to or how many people said they fell into that income bracket given a particular religion. And this comes from the Pew Research data. And you can see that this is a very compact way of viewing our data because it can fit a lot of stuff on the screen, right? So this is a format that's either really good for tables in a paper, or if you're manually tallying things, this is something that would be much easier to figure out how you can input your data or find mistakes. But if we wanted our data set in the quote-unquote tidy format, this is the format that we would want it in. We would want a column called religion, a column for income, and then a column for frequency, right? Because before, if we looked here, each column is not a variable, that it is an income bracket, which is part of the income variable, right? So this is the format that a computer would need, because now you can say, oh, I want to, predict the income bracket given a religion, right? So like that's something that doesn't really make sense as a research question, but that is now something you can ask, right? Or you can say, I want to group by religion and give me the sum of the frequency, and then you'll get the total number of respondents for each religion, right? Or you can say group by income, sum of frequency, and you'll get the total number of people in income, right? And so that notion of going from wide data, which was the first portion, to long data is the first thing I'm going to show you, right? And so I believe this does go into a GIF. And so this transformation really is taking the same bits of information and really recombining them in another format. And in Excel, you can do a transformations very similar to this using, I believe it's the pivot table can let you do something like this. So this is the first thing that we're going to cover. Okay, so let's go back into R, and we are going to open up a new R script, and just to make sure we're on a brand new clean slate, and as a good practice, we're going to click the session button on the top and then hit restart R. And what that's going to do is make sure that all the libraries that we have loaded and all of the data that we have loaded are cleared. So we're always starting from a clean slate. And because we're starting from a clean slate, we're going to load up the tidyverse library again. We're going to use the read_CSV function, And in this case, we're going to go to the data folder, and now we're going to go to the data set that's called tumor growth underscore long.csv. This is the same tumor growth data. Technically, it's in wide format, but this is the example of turning it into long format, so I named it long. So this is the same format of data we had before, and we're going to name this the variable tumor. And you can see now on the top right corner, we loaded up the tumor variable, and it contains that data set. And this data set is pretty much the same format of the Pew religion data set from before. You can see that for each column, we have the day of the study. So it goes from day 0 all the way to day 28 is the last day. And you can see what we really want is a column that's group, a column for ID, a column for day, and a column for size, right? So that is the original tumor data set that we've been working with. And so when you're going through the data cleaning process, I find it super helpful if you literally take out a piece of paper and a pen and you sketch out what are the columns you expect. Sometimes it's really jarring to be given a brand new data set and you're just wrangling with like, finally I got this thing loaded. This thing has 32 variables, but think about the problem that you're trying to answer and then literally draw out like, I want a column for a group. The problem I see here are these numbers. So I really want a column called day and then a column called size. And then these values go into the size column. And so the function that does this pivoting is a function in tidyverse called pivot longer, right? So you can think that we have this column or this data set with a bunch of columns, so it is quote unquote wide, and we want it in such a format so it actually has more rows. So we're going from wide to long, so the function name is called pivot longer. So pivot longer works just like the select and filter columns, where the first thing it takes is the data set that we're interested in. And so we can write tumor and then this piping notation into the function called pivot underscore longer. The way pivot longer works, if we go back to the example data set we have, is first we need to tell it, hey, which columns you want to pivot into the longer format. So the columns we want are all of the columns from 0 all the way to the end of our data set, right? So this data set sort of is nice because we can say like start here and then end there. And so there's a few ways we can specify like the starting point or the ending point. And so one way we can say start from the column that starts with the number 0. This part of the syntax is a little weird because technically you can't have a variable that begins with a number. And so just like before, if you have spaces in your variable name, you have to use this backtick. So this is the key to the left of the number 1 on a US keyboard. So we have to write this column as if it has spaces. So we use backtick 0 to say, hey, we want the column that actually has 0 in its name. And then we can use this colon notation as a selection. So like from 0 all the way to the last column, right? And so instead of manually typing in, scrolling to the right, typing in 28, which we could say all the way to 28. To make our data set a little bit more robust, let's say our data set or our study starts to go to day 29, 30, 31, 32, and we don't want to miss that in our analysis because it's going to be super common if we just say 28 and then the data set updates to 40 and then we run this code again and it's still hard coding the 28. So one of the helper functions, and there's a lot of these helper functions, is this function called last underscore column. And so what this allows us to do is specify the last column. And if we run this, what it did was it took all of the columns from the column that began with 0 all the way to the last column and then pivoted it into a longer format. And you can see here that this essentially gives us the data set that we want. We have a data set called group, a data set for ID. By default, it gives us a column name called name, but we know that represents day. And then by default, it gives us a column name called value, but we know that is the size variable. And so I'm going to copy this one more time. And the way we can specify this transformation, this by default gives us two default column names, but we can say there's a parameter. So if we give it a column to say, hey, we want to give this function more things, if we hit give it a comma, there is a input called names_2, and if we give that the variable day, and then there's another parameter called values_2. We can give that the value called size. And now if we run this, you can see that this overwrites the default name and value columns, and it gives us day and size. And so as you're cleaning your data set, it's also pretty important to go through and clean up your column names if you can. And so just to go back to that process is we went from wide data to long data. So what it did was for each column, it turned that value into a separate row. And then for that value in the row, it moved that into a separate column as well. So this is the relationship of the pivot longer function that we just did. And once we have this data set, we can save this to a variable. So we can say tumor_tidy. And just like how we assigned a variable to something we loaded in, we can now take this cleaned up data set, and now we have this tumor_tidy data set that we can either save out to a data set that can be the next step in a pipeline, or we can start doing some kind of analysis on it. So one thing that we can do is we can now say from this data set, group by, we can now ask the question like for each group and each day, what is the average size, right? So we can now say for each group and day, so day this time is a lowercase d because that's what we gave it in our data set. We can now say summarize, so average_size, we'll call it, is equal to the mean of size. So if we run this, you can see for each group and each day, it's giving us the average size of the tumor. And because we have multiple patients in each group and each day, some of those patients don't have a value for it. And you can see that if we don't have a value, there was a question on Tuesday about missing values, it shows up as an NA missing value in R. And the tidyverse stuff is nice because when it's actually missing from R's point of view of missing, it shows up in red. And this is to separate it from like the actual characters N and A. So when we're given the mean function, if we say, give me the mean of 1, 3, 5, it's going to calculate 3, and it's going to calculate the mean of it. If we, for example, say, give me the average of 1 missing 5, it's going to give us NA because it doesn't know how to handle that missing value, right? You don't want it to say like, oh, treat all missing values at 0 because now we have 0 that gets averaged in, and that's typically not what you want. So how do we tell the mean function, hey, drop the NA values, like pretend that the NA value isn't there? There's a parameter in mean. So within the mean function, we can say NA.rm is equal to capital letters TRUE. And this says essentially RM is the computer science-y way of saying remove. And so this is saying for the mean function, remove the missing values because by default it's set to false. And now we can say for each group and each day, the average tumor size across all of our patients. The problem here is this character, this day, isn't actually sorting properly, right? It's sorting these numbers or this value as the characters and not actually as numbers, right? So 0 comes before 1, but 1 0 also comes before 2 because it begins with 1, right? So think of a dictionary sort, not a numeric sort. So there's more data processing that we need to do. And so the next function that I will show you in the data processing pipeline is there's a function called mutate that comes from the tidyverse. And what mutate does is it allows us to modify a column. This can mean we can create a new column. So let's say we wanted to calculate drop all of the, round the size. We can create another column that's like size rounded and then create a new column that way. So that is a mutation operation. We can also mutate columns in place. So the thing that we want to do here is turn this characters, this says CHR underneath, turn this character representation of day into a numeric representation of day. So we can say we want to create a new column, or in this case, replace or create a column in place. We're going to replace the day column with the numeric version of the day column. And so how do we convert from character to numeric? There is a set of function that begins with as period. So we can say as dot numeric and then give it the column day. And what this will do is now you can see under day, it is now known as a double. So a double is a computer science way of saying that this is a number that has a decimal point, potentially that is a large decimal point, like many decimal points, is called a double. And so this line of code took the day column, which was originally a character, and then using the as.numeric function, converted it into a number. And so now the problem here is we want to sort this. And so the way we can sort this is using a function called arrange. So we can now pipe this into a function called arrange. And how do we want the sorting to happen? Well, we want to, for example, arrange by first, sort by the group, and then by day. And now if we run this, we get our data set sorted in the way we want, where it's sorting by group and then by day. We can also flip this sorting around. So maybe we want to sort by day first and then by group because we are actually curious on how the different tumor sizes change across each day. So we can do that sorting as well. And so that's the benefit of converting something into a tidy format. And that's something that we couldn't really do in the original wide format from before. And so this type of problem that we just solved is the problem where we have values being stored in columns instead of variables, right? So if we go back to the original tumor data set, the problem that we had was the 0, 1, 2, they were actually values, not an actual variable. So the values were stored in the column and not instead of variables. And this pivoting operation allowed us to turn the values that were stored into columns into a proper column. So the question I got was regarding if you imported a data set, how does it handle missing values? So the read CSV function, if you put your cursor right before the opening round bracket in read CSV and hit the F1 key, it'll automatically in RStudio open up the help page for that function. And if you scroll down a little bit, there is a portion here that says read_CSV. And in here, there is a parameter called NA equals, and then it says, if the CSV function that you're loading has the characters NA or an empty value, treat it as like the special missingness in R. And so if you have, if you want to get rid of the NA character string because it's something that's actually NA, like North America, don't do that. You can remove that in your data set. If you have 88s or 99s, you can pass in another parameter. How to handle those values. And the other question is, how does it handle the missingness in mean? So I can show you, let's say we take the mean of 1, 3, and 5. That was the example before that I was giving. It gives us 3. But if we say 1 NA 5, what it's actually doing when we're saying na.rm is true is it gives us 3 because it's essentially dropping the value. What it's really doing is it sees the 1, it skips over the NA, and then adds in 5. So it's 6 divided by 2 is 3, and it's essentially pretending that the NA value isn't there. So this is very different from treating the NA as a 0, right? Because if the NA was treated as a 0, this would be 6 divided by 3, which would give us 2, and that's not the actual mean of our data set. Okay, so the next thing is a really short exercise, and we'll also use this as a break. So the exercise I want you to do is, there is a data set in our what is it called? Do I not have it in here? Actually, maybe I don't have it in here. That's interesting. Okay, I mentioned a break, so we'll take a 5-minute break. So we'll come back at 53 to the hour. And if you have any questions, you can let me know from there, and I will put a 5-minute timer for a break. Is the question just how to recode a 0 or a particular value to NA? I'm trying to like rephrase the question.
Yeah, that's I don't know if you can hear me, but yeah, it's basically
Yeah.
turning for certain columns, you want a 0 to instead be an NA. So not for the whole data set, but just for certain columns.
Yes. Okay. So what I did, I literally so tidyverse is nice because it is much better of a Google term than the letter R. So and this is literally like things that I like. I know that these things can be done, so like I pretty much never remember how these things are like actually used. So there is this NAIF function. There's also this recode function that you can use, and if we look at it, part of the example is you can see here they use this Star Wars data set. We saw select and then mutate. So this mutate is how to convert a column in place, right? So if you want a particular column, you can run mutate. And then they're saying for the column for eye color, if the eye color has for the column eye color, if it's oops, that is the alarm. For the column eye, yeah, if the value is unknown, give it the recode it as NA. I believe that is what that is saying. I actually usually use this recode function, which essentially lets you recode arbitrary things, not just things to NA. And so this is a function that says, you know, and this happens a lot in survey data where you can have, like one of my survey questions was, are you a physician? Are you a nurse? Are you a PA, et cetera, et cetera? And I use a recode that essentially says if the value was physician and if the value was nurse and PA, like recode all of that into like clinician variable. So you can do that as well. All right, so hopefully that, and like simple things like this, like if that's all you use R for, like I would say that is always a win where like you've slowly like made your data pipeline a little bit more reproducible instead of relying on weird find and replace operations, which are kind of terrifying. Mainly because when you do these find and replace operations on the raw data set, there's no trail that ever like 3 weeks from now or the next day that you've done that operation. Okay, so the next problem that we can have is multiple variables stored in one column. So this is an example from the paper, and this is a format of data or data format that's super common in healthcare. And we have for a given country in a given year, for a given male, so the first letter is gender, and the next sequence of numbers is the age group. So how many tuberculosis counts there were in that country for a particular year. And you can see it goes from male 0 to 14 all the way to males unknown, and then there's another set that goes from female 0 to 14 to females unknown. And so this, again, is a data format that if you're curating data or if you need to put it into a report, this is a data set that is very useful because it's very compact. But if we can't ask any of those summary functions that we wanted, right? So maybe we can say like, what is the total number of males 0 to 14 we have in this data set? We can pick this one column, but we can't really say, you know, what are the total number of people from ages 0 to 14? We would now have to select these two columns, right? So And if we're trying to do some kind of analysis, like how do we, for a given country and year, can we essentially fit a line through how many cases there are, that becomes more difficult plotting wise, because we have to now process this data a little bit more. And so remember when I said when you are given a data set, if you're stuck on how to do the processing, try to disentangle the data coding portion with this is the output of data I need. And so the output of the data that we would want is we would want at the end of the day a column for country, year, sex, age, and cases. The way we can get there is actually this intermediate step, which is very similar to the process we just did before, which was to take those M014 all the way to males unknown, from female 014 to females unknown, like from that point all the way to the end of our data set. We essentially just want to pivot it longer to get this data set on the left, right? So that is one step closer to what we want. And then how do we get from the data set from the left to the right? Well, forget about programming, because there's always something that you can learn, but like how would you using heuristics like split or go from the data set on the left to the data set on the right? You might say, hey, there's this value, this column called column, and if we essentially pluck out the first character, that can be the sex column, and then keep everything else for the age column. We can do that. In this example, we're not exactly going to create the age column because it's going to need a little bit more processing, like putting the dash in there, but that's for like another class on like more data processing. And so how do we do that? Well, we need to first load up a data set for that. And because that data set is actually health related, we can load up that exact data set from the paper. So we're going to load up a data set called TB, using the read_CSV function, just like before. This is going to be in the data folder. And then the file that we're looking for is TB, I believe it is TB long, because this is the example we want to convert into long format. And if we look at it, this is the exact data set from that paper that we are going to work on. And so remember the steps that we need. If we first look at this data set, the first problem that we see is that M0 to 14 all the way to these columns look like the same problem as before. There are values stored in our column. So forget about what that actually means. Let's just fix that problem first. And so that bit of code looks exactly like the code that we did before. So we can say TB pivot longer, and we can select from M0 to 14 all the way to the end. Instead of writing that same bit of code, there is another way you can run selecting columns. And in one way you can also select these columns, and this is also useful for survey data, is we just want all of the columns that begin with M and begin with the letter F. So we can actually do a selection based off of that criteria, right? So in survey data, it's also really common, like, I want all of the questions that begin with Q 1.3, and because 1.3 has a bunch of sub-questions with it, right? And that's all I care about. So I can say, like, starts with Q 1.3, and it filters my data that way. And so we can use that same technique with the starts underscore with. And then there's also things like ends with or contains. So there's very different ways you can specify patterns. And these are all different ways to make your code a little bit more robust, because now you're not saying like start from this column and end at that column. If you make your column selection a little bit more general, you could potentially have your data set work better as the data updates. Or you can end up, if someone just so happens to create a column called like month, that's something you're going to have to deal with because it also starts with the letter M. So we're going to use the starts with function, and we're going to pass it multiple things. So in R, this C function for concatenate is how we tell R we want multiple things, right? So in my mean function from earlier, I used mean of 1, 3, and 5, and you saw that I used this C function because I'm trying to give mean multiple numbers, and the way I give it multiple numbers is using wrapping it around the C function. And so now with starts with, I'm trying to give it multiple things, and so we use the same C function with it. And so now I'm saying starts with M and also starts with F. And so now if I run this, we get that intermediate data set that we're looking for that has a column called name, a column called value, and then the M014 all the way down, and then the value there is. So that's good. That's most of the way there for the data set that we need. So we can save this to tb_long, save it to a value there, and now we can work on the second step. The second step is we can now take that function, and there is a function in tidyverse called separate. And what this does is you give it a column. So in our case, the name column is the column we want to do our separating. And what do we want to separate this column into? Well, we give it the parameter into, and at the end, we want a new column called sex and a new column called age_group. And the way we want to separate it, we can say SEP is equal to 1, as in take the first character and pluck it out. You can also, for example, if you have a comma delineated string, you can say sep is equal to like a comma or an underscore. And so these are techniques of when you are curating your own data set, try to leave yourself breadcrumbs on how you would process this later on, right? So even if your data set, because it's easier for you to input M1524, just know, hey, when I want to process this, I need to pluck out the first number. Or it would be M_014. Or it would be M0_14. So now you're leaving yourself breadcrumbs of the first character represents sex, and then I have a block for age group with a dash into it, and then that dash will split into the lower bound and then the upper bound, right? So always try to think about how you can leave yourself breadcrumbs, because all of these functions have ways of handling these little problems with your data. And so now if we run this separate command, we're splitting that name column into two columns called sex and age group that show up here. And the way we're separating that name column is by plucking out that first character with sep equals 0. And now we have a data set that now has everything that we need. So now we can go through the process of group by the age and then calculate the total sum of the value. Or we can say, for each year, give me, for each year and age group, so that's another group by year, group by sex, or group by year, group by age group, give me the sum of the values. And we can do that as well. So as you're curating data sets, think about how you can leave yourself breadcrumbs, because I do this as well when I'm putting together data sets, because it's easier to input data into a spreadsheet in one format, but I know I can use these dashes or underscores or positions in characters as a way to clean my data. And the last example, so that is how we can deal with multiple values being stored in columns. There is another problem that we can have of being, and this is also in Hadley's paper, of variables being stored in both rows and columns. And so this is an example data set where we have, for a given ID, year, month, temperature, min and max, and day, what that temperature reading was. And you don't know that this is the actual problem, that being variables being stored in both rows and columns right away. the first thing that we know is we see this D0, D2, D3, all the way to D whatever. We know that is the same problem we've been dealing with this entire time. That should be a column called day, right? And at the end, maybe we don't realize that we have this other problem. So we say like, okay, let's fix that problem first. And once we fix that problem, we end up in this situation on the left. For each particular day, we have a temperature max value and a temperature min value. And the way you realize that you have this multiple data storage problem, like values are stored in columns, but they're also stored in rows, is if you ever encounter a data set where a bunch of values is repeated except for like some measurement, then you know that you have this new problem. And so in our data set, the ID date column are going to be repeated in duplicate. And the only reason they're repeated is because we have this temperature min and max value. And so what we really want is to have a column called T max, a column called T min, and then a particular value. And now we have a lot less duplication in our data set. And so we can load up an example data set for this as well. The one that we have is the CMS utilization data set. So we can say CMS gets a data set, reads underscore CSV. It's in the data folder, and it's called CMS underscore utilization.csv. And if we take a quick look at this data set, this is a data set that I know that there are people from like outside of the United States in this workshop for the first time. This is very United States centric, but for a particular state, a particular FIPS code of a state, so that's more or less like a census term, for a given per capita count for gender, age group, number of chronic conditions, how many people there were for each year. So that's what this data set is. And so we have the same problem as before, is that we have these year columns that represent, this is not counts, this is number of dollars spent for that particular group in year in the CMS system. So the first problem that we have is that the years are in columns, and this is great if we want to look across to see how something changes over time very quickly, but it's not very useful for our data analysis point of view. So we can fix that same problem. We can fix this problem the same way we have been fixing it. So we can say CMS goes into the pivot longer function. And I'm going to say start with 2007 and then going to the last underscore last, LAST, last column. And I can say names underscore 2. I'm going to turn those column names into a new column called year. And so now we have for state, FIPS code, all the demographic information, year and value. The other problem, so let me save this to a CMS underscore long. So that is our first step in processing this data. The next thing that we'll notice is this variable, we have a count for a particular sex age group, like per capita spending actual. And we also have per capita spending standardized. We have ED visits per 1,000 beneficiaries, hospital readmissions percentages. But the problem is if we look across the row, for example, the values for Alabama 1, males less than 65, 4 to 5, in 2012 is going to be repeated, I believe, like 4 or 5 times because we have 4 or 5 of these variables in here, right? So that is sort of the like code smell or like odor of a bad data set, or something's not formatted correctly in your data set. is when a bunch of values in a particular row, are being repeated. Sorry, it's CMS long. And so maybe this is the data set that you need, but eventually if you were to try to plot like, oh, give me the average, like if you say group by year and give me the average value, it's incorporating these other variables, and that's not something that we want. And so the way we sort of do that other task, so the problem that we have now, before this entire time we were going from wide data to long data. That means converting columns into a variable and creating more rows. We're now trying to do the opposite transformation, where we're trying to convert a single column and split those values up into separate multiple columns. And so the function that we use for that, so I'm going to say CMS long, is actually this function called pivot wider, which is the opposite of pivot longer. And the way we use pivot wider is we specify two variables. There's a parameter called names from, and what this is doing, and this is exactly how pivot tables work in Excel, you pick the column that you want to pivot out. And so names from, we're going to select the variable column. And then values from is when we take each unique value in variable and pivot it out, what is the column that we're going to use to fill in the table? And so in our case, this per capita spending refers to this value column, and then same for number of admissions per 1,000 or something. That is this value column. And so that is the column that we're going to be using, value. And so now if we look at our data set, a little bit easier if I save it to CMS underscore tidy. Now if I look at my data set, we also have this age group variable, but for Alabama, which has the FIPS code of 1, for a particular year, we now have these 4 variables: per capita spending, standardized ED visits per 1,000 beneficiaries, and hospital readmissions percentage, right? And so now we can do this thing of group by the age group, group by the year, give me the total per capita spending across all of my states. And now that is a question that we can answer a little bit easier than before. Yes, you could have kept you didn't have to go through this pivot wider function, and you could have also just grouped by that variable, but this is something that you might want to think about as you're trying to work with your data set. Sometimes one data set is going to be more useful than the others for one reason or another, and so this is something that you would need to think about. Okay, so that really is this is the main point of how you can clean your data. Granted, like once you do these pivot steps, there's always going to be more like mutation steps where you're processing your columns a little bit more. For example, I have a bunch of zeros and I want to recode them to NA. Well, you first need to get your data set into a situation or format where you can select a single column to do a mutation, right? So this tidy data principle is fundamental to how you can work with data, either for plotting, for model fitting, for additional processing, et cetera, et cetera. And so I guess the main takeaway here is whenever you see a data set, think about how you can make it tidy, or if you're curating a data set, maybe have it be tidy to begin with. But once you have a data set that is in tidy format, it is much easier to work with and do other calculations. And if all you use R for is to pivot a few tables and then load it back into Excel to do Excel sheet tables things, then that's okay. All right, so the next thing that I want to go through is visualizations. And I want to go through this very quickly on how we can start using ggplot2 as a visualization library in R. I'm going to go through the visualization part very quickly because I want to go through the next part, which is logistic regression on fitting a model and how we can, for example, plot the coefficients or the results of a model using ggplot. So ggplot will be very quick, but we'll come back to it at the very end when we're trying to do the whole plotting with a logistic regression model. And so when we're thinking about data, you saw before that we had a column of data that was character values and we needed it to be numeric. We now need to think about, for each column in our data, like what is its actual type? Type as in, like, is this storing a number or is this storing a character string? But also types in terms of, like, is this a nominal variable in terms of there is no order? So, you know, what treatment group you're in doesn't really have an order to it, right? It's like the treatment group doesn't really mean it's better than the placebo group. So the 0-1 encoding for treatment group is nominal versus ordinal, which is, you know, like a Likert scale where you have rate this thing from 1 to 5. That has an inherent order to it. And then a special type of ordinal variable or nominal variable is a binary variable where you're just saying this thing is just one of two options. In the biostatistics health context, this binary variable is probably the analysis or variable type that's used most often because it is essentially the question of yes or no. Did this person get better after taking treatment, yes or no? Did this drug test identify your status like correctly, yes or no? Or did I get cancer, yes or no? Or did this person die, yes or no? That is a binary variable, and that's why logistic regression ends up being a very popular tool, because a lot of medical questions can be rephrased into a binary context. And so once we understand how what types of variable are, let's go into the process of using ggplot as a visualization library. The way ggplot works is a layering system. And so we start from the bottom and then we add layers on top. So the first thing we need to provide is what data we want to plot. The mapping is how do we take the data and map it to parts of our figure. For example, we have this data set. What variable are we mapping to the x variable, what x axis, and what variable from the data layer are we mapping to the y axis? And then we can do things like what variables are being mapped to the size of, if we're using circles, or shape if we're trying to use different shapes. So mapping is how the data itself connects to different aspects of our figure. And then there's things like statistics. So most of these statistics are going to be calculated for you by default. So for example, if you're trying to draw a bar plot of counts, by default, the statistic is going to be sum. But you can always say like, hey, this is a data set that already pre-calculated everything, so the statistic would be like the identity. Scales are things like, do you want to draw your plot on a log scale or not? So different types of scales. And then the more important thing is this geometry layer, because the geometry layer actually says, given a data and a mapping, what is the actual plot that you're trying to make? So a geometry layer would be a bar plot, like we're trying to use a bar geometry. That's sort of the ggplot lingo. Another geometry could be a point, because we're trying to make a scatter plot. And so that is the geometry layer. On top of the geometry layer are more just ways of making your plot look prettier. The top layer is themes that really make your plot prettier, but the facets layer is probably the reason why I use R and ggplot no matter what programming language I'm using to plot my data, think of the facet layer as the group by operation when we were trying to do summary statistics. So now you can say something like, I want to calculate, or I want the figure of age versus tumor size for each value of treatment group. And that for each value of treatment group is that facet layer. And so you don't have to create 4 plots individually. You can say facet on this one column, and then you have 4 plots drawn for you. And so that is the quick intro to ggplot. And let's go through some examples. What I'm going to do first is this tidy script that we were working on. I am going to call it the next number, call it 04 tidy. And we are going to create a new file and call it 05 ggplot. And what I'm going to do is go to session and restart R. And we're going to have to load up a couple more libraries in this case. So we're going to have to use tidyverse first. Tidyverse, we're also going to have to use ggplot2 for our plotting library. And Peter Higgins is with us today. He maintains this medical data library, which is a R package that contains real medical data from studies that we can work with. And so using the medical data, once we have this medical data library loaded, there's a function, there is a data set in here called blood storage. And so this is a retrospective cohort study of 316 men who have gotten their prostate removed in a surgery. And this is a study that is trying to look at 30 days if they have a biochemical marker for cancer reoccurrence within 30 days. And the main thing that they're looking at is if the blood transfusion during the surgery was stored for a prolonged period of time, if that affects the cancer resurgence rate. So hopefully I got that correct. Since Peter's here, he can probably correct me if I got that wrong. But this is that data set. And so when we're looking at our data set, one of the sort of like process steps that you use when you're going through data is maybe you want to look at the column names of just the column names of our data set. So we can say something like names of blood storage, and here we get just the column names of our data set. And I believe I mentioned this on Tuesday, but looking at names of a data set is a really good way, especially if you know that the incoming data set was hand curated, because it puts in quotes exactly what's in each of those columns. And it's very possible if you're looking at data in an Excel sheet that maybe you have a couple of spaces before or after a particular column, and you won't really see that when you're looking at the spreadsheet. But when you're trying to pull up an actual column, it's not, age, it's really space, age, space, right? And that's going to cause havoc for you. So looking at names is a great way to make sure that the column names are loaded in correctly and is exactly what you are expecting. So now when we are working, so remember the different layers of ggplot. And one of the things you want to look at when you have a particular study or analysis in mind is you want to look at the outcome variable. So in our case, the recurrence variable is the variable that tells us whether or not a particular person has had a recurrence. And so that is the variable we want to plot. And so we'll go through the separate layers of ggplot. So we can say ggplot. We're going to say data is blood storage. And if we run that, all we get on the right-hand side is an empty canvas, because all we did was saying, hey, plot this data. We haven't given it any mapping, and we haven't given it any geometry. So I'm going to copy and paste each one of these steps, but you would probably end up building this all up in one go. So the next thing that we want to specify in ggplot is mapping. So the syntax is a little bit weird, but the mapping uses a function called AES for aesthetic. And in here, we can say x is equal to the recurrence variable. So now if I run this, again, all we get is this x-axis that says recurrence, but because we haven't specified what we actually want to plot, there's nothing that has shown up. So the next thing that we want to do, remember the layering system. The next thing we want to do is add a geometry layer. And the way we do that is we literally use the plus symbol. So think of the plus symbol as that piping operator from before. Because of the time ggplot was created, like in the late aughts, there wasn't a concept of this pipe operator. So Hadley had created this plus operator to work with plots, so adding layers. So we want to create a bar graph. And the way we can figure out in ggplot like what all the different types of geometry objects there are is if we say geom underscore, and if you hit tab or maybe it shows up automatically, these are all of the different plots or geometry objects that you can create. And so you can see in here there's histogram. You can literally just draw a horizontal line if you need it as a reference for something. You have area plots. You have density plots, etc., etc. The one that we're going to be using is bar for a bar plot. And you can see here, once we run that, what it did was it took the recurrence column, which is a bunch of zeros and ones, and drew a bar plot on it. And bar by default, that statistic is summing. So it is the count of all of the zeros and all of the ones. And so we can use this system essentially to create multiple plots. So it's always really important to look at your variable of interest, your outcome variable, for instance, because in this case, one of the problems that we have in this particular data set is there are a lot of zeros than ones, right? So you can think of this as when we start fitting a model, this could potentially be a problem because this readmittance is pretty almost like a rare occurrence. And this is a problem that happens pretty often in a lot of medical data sets because a lot of these diseases are rare outcomes. And so this class imbalance is a totally separate topic, but this is something you want to be very mindful of. So other things that we would want to plot are things that we might think are related. So this is part of the data exploration phase that we're going through. There is a data called age, and maybe we're saying maybe age has a factor to deal with the outcome. And so we would want to take a look at the age variable. So how would we do that? So we can say ggplot, the function. Data is the blood storage variable. The mapping is the aesthetic, where x is equal to age. And then we can add in a layer for geom underscore histogram. And what this will do is, since age is a continuous variable, it's going to create a histogram and start binning the values into a histogram for us. If you have a large spread, by default, it will create at maximum, at most, 30 bins. But we can change that behavior if we want to. So I can copy this line, and within histogram, I can say bins equals 10, for example. And now I have a histogram with 10 bins. If I need more than 30, I can put in more bins if I need to. And then just for the sake of time, I will go through sort of like the notes that I have on the page. But you can also create box plots. So let's say we have total volume and age. You can say for each value of total volume, give me the box plot for age. There is this notion of a factor. So things in your data set. So this is one of those side effects when you're not using R and you're getting data sets that are made for like a statistician who doesn't want to clean any of your data, just wants the final data set so he can analyze it. And that's why you have things like code books, and then your data set are all like these numerical codes. R gives you the benefit to put the actual code in your data set, so you don't have to refer to a code book. So like you can actually have something that says male, female, other, versus like 0, 1, 2, right? And then constantly having to refer back to a code book. That's one of the nicer benefits of dealing with or working in R. But if you are given a data set where, you know, total, like a thing is only given as values like 1, 2, and 3, like this total volume variable is, you know, if it's from this size to this size, it's considered small, medium, or large. Categorical values are known as factors in the R world. And so just like before, where we talked about as.numeric to convert something from a string to a number, we can use as.factor to convert this thing into a categorical variable. So now we can see R will now treat 1, 2, 3 as separate categories. So think like ordinal or discrete variables instead of the numbers 1, 2, and 3. And so we can create box plots and stuff like that. For box plots, I like this plot called a violin plot because box plots for me have a tendency to hide its skewness. It's not as obvious, right? So like if I look at this, can you really picture like, do all of these things look normal, or like pick one of these bars that don't look normal to you? Versus if you draw the violin plot, which is really think of it as a histogram on its side that's mirrored across the center. It's more obvious to you whether or not your data is normal or not. And then remember the layering system. In this example, I'm plotting a violin plot, and then literally on top of it, I'm plotting another layer on top. And that's really the cool thing about ggplot is you can plot multiple things on at the same time, right? And so putting the plots on top of a distribution plot is really useful, and it's really drawing two separate plots at the same time. Instead of just putting on the points, there's another type of geometry called a jitter plot. And all this is really doing is instead of drawing all the plots in a straight line, it's randomly scattering it, just so you can get a sense of the density at a particular location. You might find this useful, you might not, but the main takeaway is maybe you want to have a bar plot with other points on top of it, right? Like maybe you've also calculated, you know, the mean. So now you want the bar, like a histogram, but also a dot for the mean or something. As far as aesthetic mappings go, I only talked about X and Y, but there's other things like color and fill and shape. And just like specifying the X variable, the Y variable, you can specify a color or a shape straight from your data set. And without too much effort, you can create different colors. Use another variable, like another categorical variable, for a color. And, you know, this is the same problem we had before. We have to turn this variable into a factor because it's treating it as a continuous variable, et cetera, et cetera. But the most important thing I want to show you, and this is the thing that I'll cover manually, is this facet, right? So let's create a scatter plot. So we want to look at ggplot. Data is going to be, instead of always specifying data equals, because ggplot already knows that the first parameter is going to be our data set, we can say blood storage. We can then say AES directly instead of saying mapping equals. And now we can say X is equal to, for example, the volume. Y is going to be equal to this variable called pre-op PSA. And then we can specify something like color is equal to this other variable, and then give it a geometry of, and I'll paste this into the chat. So this is the last example that we have. The problem here is we actually wanted this to be a factor, like counted as a categorical variable. So we would have to write as the factor of that. And let me put a few line breaks so this all shows up on the screen. All right. So the really nice thing with a facet is, let's say we have this variable called this other variable that's like the age of the red blood cell. So we can say facet wrap. The notation's a little wonky, but we use this tilde. So this is shift and then the key to the left of the number 1. And then we can give it the name of the column. So rbc.age.group is the variable. And what this will do is for each value of the red blood cell age group, it's going to draw up that scatter plot for us. So what that one line in our ggplot code is doing is essentially filtering by the age group of 1 and then redrawing the scatter plot, and then filtering by age group of 2, redrawing the scatter plot, filtering by 3, redrawing the scatter plot, and then putting all those scatter plots together for you at the end. And if you need multiple variables, instead of facet wrap, I'll copy this little bit of code again. If you have 2 variables or 2 categorical variables that you want to look at, there's another one called grid. And then you can put in to the left-hand side and the right-hand side of that tilde the outcome that we're looking at, which is the reoccurrence. Then we have the red blood cell age group, and then the actual volume and pre-op PSA values that they're using to figure out if cancer has reoccurred. And so this is a really good way to very quickly figure out what is going on in your data set without having to manually draw subplots by yourself. And this all, again, ties back into our spreadsheet lesson and our tidy data lesson, because the reason why we're able to do this is because all of our columns in our data set are proper variables, right? We can now pick out a single column and say, hey, I want you to do this calculation with this column, right? We don't have, the different age groups in 3 separate columns. They're all in one column because that's the actual variable name. And these tidy tools, or a lot of these tools, are built around the fact that your data set is tidy. And so you're allowed to do these types of operations. Okay, so let's take a 5-minute break. If you have any questions, let me know in chat or post them. I did not see any questions so far, but let's take 5 minutes and then we'll finish up with logistic regression, and then how we can go back into plotting after fitting a model. So it is going to be roughly 46 of the hour, but I have a timer up. Okay, so last chapter for this workshop block. I'm going to very quickly try to teach some statistics in the next half hour. It is going to have very little theory, but it's mainly trying to tell you that everything really is just drawing a straight line. So we're going to be talking about logistic regression. And the reason why I picked this as the first statistics related topic is it's the most common used model in the health sciences. If you ever take a machine learning course, it is probably the first machine learning algorithm that you will be taught, especially if you take Andrew's ML course through Coursera or one of those other online MOOCs. And essentially, logistic regression is a model that works on a binary outcome. And so even if your variable or your data set doesn't have a binary outcome of interest, so maybe you're looking at, healthcare expenditures in your particular county, what you might do is you might take the data set that you have, calculate the median of, and then split it such that you have below the median and above the median as low and high. And now you've created a binary variable. And so that's all part of like some data processing that you'll get into your model. But at the end of the day, you have some column that you can point to that is a yes or no. And so logistic regression is a form of linear model. So we all remember the y equals mx plus b from the first time we've taken a math course where we drew a line. And essentially, this y equals mx plus b, when we want to specify a linear model or a logistic model or any of these linear models, is really adding more of those mx parts. So this b is the intercept, and then we are saying mx1 plus mx2 plus mx3, etc., etc. The m and the x in statistical language end up being called, the m part ends up being called a beta. So when you hear people talking about beta coefficients or betas, they're literally referring to that m part of the linear line. And so the way we add variables to our model is we are literally adding more of those beta x components. So beta can be referring to, in our case, the age, the volume, the pre-op PSA, and other variables, and we just keep adding them on. And then at the end, we say we run that model through a linear regression model or an algorithm, and we get this value at the end that essentially will tell us, some probability of something happening given some value of x and the calculated value of our coefficient. So in all models, in our case, our linear or our logistic regression model, we take our data, we feed it through the model, it gives us these values for beta, and then we give it another brand new variable. So let's say we have a value for beta that's like 3. And then we have for a brand new incoming data set, we have an age of 65. And so what we are literally doing is we take 65 multiplied by 3, and that's how much it contributes to the overall model. And then we add up all of those components, and then we eventually end up with some kind of probability at the end. And so that's essentially how linear models work. The difference between a linear model and a logistic regression model is that a linear model draws a straight line, and we all know lines just go on to infinity in both directions. A logistic regression model, it won't make sense to draw a straight line through 0 and 1 because, for example, 1.5 and 2 they're not even options, or they're not part of the variable that we're looking at. So we need to draw a different type of line. And so that's why it's called a logistic regression curve instead of a linear regression line. And this is really just this slide is really just a fancy way of saying, how do we go from a straight line to a curved S-line? And it is through this process called a logit function, which is really taking the log of the odds over probability over 1 minus probability. And that's why at the end, you talk about odds ratios when you talk about logistic regression models, and it's because of this transformation that's happening. So essentially, in logistic regression, we perform this logit function, we draw the line there, and then when we want to interpret it, we undo that logit function, and then what we're left with is an odds. And so that is why our logistic regression output are called, we work with the way we interpret them are in odds ratios. And so that is all the statistical theory that we're going to go through. And we are now going to create a 06 dash, we'll call it logistic. And I'll show you how we can fit a logistic regression model in R. I'm going to go to session and restart R. So I know that this R script is going to be brand new and clean. We're going to load up tidyverse again. And we're going to load up medical data again. And we're still going to work with the blood storage data set that comes into this package. Instead of typing blood storage, I can also redefine this as blood. And now we can refer to the variable as blood instead of blood underscore storage. So how do we go about fitting this model? It is a linear model at the end, and the way we fit a logistic regression is, in statistics term, logistic regression falls under the types of regression models called a generalized linear regression. And so generalized linear regression, also known as GLM, there is a built-in R function, and this isn't part of tidyverse. This is like you load up R and this is immediately available to you. There's a function called GLM. And the way GLM works is we have to pass it what's known as a formula. And so that's back to this tilde notation. And so remember y equals mx plus b? Think of that tilde as the equals part of that y equals mx plus b. So what is the y? In statistical terminology, y is synonymous to dependent variable, which is synonymous to outcome variable, which is synonymous to response variable. Those are all 4 ways of saying the same exact thing, which in regular terms is, what is the variable you're trying to measure? In our case, the variable we're trying to measure is called recurrence. So we have recurrence, tilde, and now we want to say what variable in our data set do we want to use to either predict or fit or use as the independent variable or our predictor. Those are also the same set of terminology for what are we trying to use to show what is related to our variable of interest. So just to make our first model pretty simple, we'll just pick a single variable called age. The next thing GLM needs is we actually need to tell it like what data set we're using. We've only given it 2 variables, so now we actually need to say, hey, use this data set. So we say data is blood. And because GLM is an entire family of different types of linear models, including the one that draws a straight line, we have to tell it to actually go into logistic regression mode. And the way we do that in R is family is equal to binomial. And that's really just coming from the statistical terminology world of how we fit a model. And once you do that and you run that line of code, congratulations, you fit your first logistic regression model. people usually talk about data science being extremely complicated, but the complication is literally actually all processing your data and then dealing with the output of your model. The actual model fitting is most of the time can be boiled down to like 1 or 2 lines of code, which is take the function that does the model that you want and you tell it like what are the predictors, what are the outcomes, and then there you go. So we can save this to a variable. I'll call this mod1 for our first model. And then you can always rerun that variable to look at it again. The way we can, if you just care about the R output of our model, or maybe you're comparing R output to like SAS output or something, if you want something more of the SAS output like that has everything in it, you can say summary of this model. So mod1. And what this will do is it will give you more or less all of the other, I'm blanking on the term, but all of the other statistics on this statistical model. So all of the, I'm blanking on the actual term, but other ways you can tell if this is a good or a bad model. Part of that output of summary is this portion here that this is the thing that, you know, makes or breaks like academic papers, right? Here are our coefficients. And so if we go back to the terminology that's used for doing this stuff, it is known as the beta. So these are why people call them beta coefficients or just coefficients. This is that B in our, or this is the M in our y equals mx plus, this is the M in the y equals mx plus b. So this is the age or the beta. And this is the actual value for that beta coefficient or that coefficient. And then we have here, this is like the p-value, and this is the thing that gets people into a lot of trouble where they end up like p-hacking and just trying a whole bunch of combinations to try and get this under 0.05. And then you can see like these dots and these stars is what gives you that notation. Oh, yeah, so we have like these goodness of fit values. So like deviance is one way to measure fit. AIC is also another way to measure fit. But these goodness of fit values, or these ways you can compare models, they always have to be used in conjunction with something else, right? It doesn't make sense to fit a model and say like this is better, because the question is always better than what. So we need to compare models by fitting multiple models. But let's just keep going on with this one small example. One thing that you would want to do is, okay, we have these coefficients, right? Wouldn't it be nice if we were to pull this table out as a regular data frame that we've been working with? Because remember, when we're dealing with logistic regression output, we have to undo that logit transformation, because otherwise the way we have to interpret this number is this is for every 1 unit increase in age, the probability of being having recurring cancer versus not recurring cancer is the log odds of 0.01, right? Like that 0.01 log odds portion of the interpretation is really weird. So we want to be able to undo it. And the way we want to be able to undo it is, it would be nice if this was a table, and then we can run our dplyr mutating function and then undo that calculation in data. And so how do we pull out this coefficients table from a logistic regression model? This actually uses a library. It comes with tidyverse, but we haven't used it yet, called Broom. And think of Broom as, the actual broom that you use to sweep and clean. And this is the broom that gets used to clean your statistical model output. That is the actual pun of why it's called Broom. And so in Broom comes with a function called tidy. And if we give tidy, that comes from the Broom function, the model that we want, it's smart enough to know that, hey, mod1 is this whole statistical output thing. I know how to pull out the coefficients table. And so I'm going to pull out the coefficients table and then give you back a data frame object. And so now this is a tibble. So this is the tidyverse way of saying a data frame object. And now we can actually save this to saying, let's call this res1 for results1. And now we can see like, hey, this actually, mod1 was this list of 30 things, but now we have 2 observations and 5 variables. And this looks like a table that we've been working with this entire time. And so now we've, fit our model, and now we can go back to the first thing that we learned of like, how do we filter things? Or I just showed you in the tidy data portion, how do we mutate or make a new calculation of something? We can now treat res1 as a data frame object that we've already been that we are already used to. And if you ever get confused with what is this thing I'm working with, because all of a sudden like these tidyverse functions don't work anymore, there is a built-in function called class. And if you give class some kind of variable, it's going to tell you what this thing is. So if we say class of mod1, it's going to say, hey, this is a linear model. It's really a generalized linear model. And that's the thing it is. Mod1 is a generalized linear model. We can also say class of res1 or results1. And now it's going to say, hey, this is a data frame object. It is known as a tibble in the tidyverse world. And so now you can be more confident that this is an object or a thing that you are already familiar with. And so if we go back to this bit of logit mathematical formula notation, remember that this logit function is called the log of the odds. And the way we want to undo the log calculation is if we exponentiate like e to the power of both sides of the equation. So this is backed into regular algebra. When what you do on one side, you do to the other side, and then nothing changes. If we exponentiate both sides of the equation, on the left-hand side, that gives us the odds. So that is something that we roughly understand, like conceptually. Odds are very similar to the probability of. There's a small technical difference, but for this case, you can say like, think of odds as the probability of. And then on the right-hand side is all we need to do is exponentiate like that entire formula, and then we can represent it that way. And so for each one of those betas, we now need to raise it, exponentiate those values. So now we can interpret those numbers not as log odds, but as regular odds. And so how do we do that? We take our data frame, and then remember mutate is a function where we can create a new calculation based off of a current variable or a current data set. And so now we can say mutate, and then we can create the odds function. And the way we exponentiate something is there's a built-in function called exp for exponentiate. And then we give it the column that we want. So the column we want is called estimate. So we can now say estimate. And now we get this column at the very end called odds, which is really the exponentiated value of the estimate. And so now we have something that we're used to reading in all of these journal articles when they interpret this value, right? So this 1.02, the way we interpret this value, and this is probably something you're gonna want to like bookmark or link or just write down. The only way that is statistically correct that you can interpret this number is saying for every 1 unit increase in age, so as age increases by 1, the odds of going from 0 to 1 in our response, so 0 to 1 in our response means going from, what are the odds of going from not reoccurring to reoccurring, increases by this number, 1.02 times. So for every 1 unit increase in age, the odds of going from 0 to 1 in our response increases by 1.02 times. So another way you can say that is the odds of earlier biochemical reoccurrence of prostate cancer after prostatectomy, like removing of your prostate, increases by 1.02 times for every unit increase in age. And that is how you interpret that number. And so when you see these tables in medical journals or in any biostatistics publication, that is how you interpret these numbers in these tables. And so let's copy this mod 1 and let's make another model. So this was a very simple model in the case where we only worked with age. But how do we work with multiple variables? Well, so remember the notation here where we're adding beta x1 plus beta x2, et cetera, et cetera. So the formula notation in R is really nice because we literally use plus and then add in the next variable that we want. So we can say, how does the volume affect it? How does the pre-op PSA affect it? And then we're still using the blood data set in our logistic regression. And now you can see we now have a second model that we have. And we can run summary of mod 2 to look at the coefficients table, and you can see that the pre-op PSA seems to be highly significantly related to whether or not the patient will have a cancer reoccurrence. And if you are an actual clinician, that probably makes a lot of sense to you. I am not an actual clinician, so it is something that I've convinced myself makes a lot of sense. But that's how you can add more variables. So let's add one more variable to this model, and I'll call this mod 3. And it's going to be the same exact code, except now we're going to add in the tumor volume variable. And the tumor volume variable is that variable that what we had to do before. It comes in as a, let me just show you this. Tumor volume comes in as a number, 3, 2, 1 for low, medium, high volume, but those are actually categorical and not actually 1, 2, and 3. So if we run this, the code is going, sorry, this needs to be mod 3. The code is going to work, but the interpretation of this tumor volume is incorrect, right? Because there isn't, because it is a categorical variable. Think of categorical, like a very common one is like age group. You're comparing different age groups. You're not really trying to compare going from one age group to another, if that sort of helps explain what we're trying to do. Like this tumor volume is really it's not a continuous variable. It is a ordinal variable because there is an order to 1, 2, and 3, but they're still distinct categories. And so this is one of those examples of like, yes, we're all very new to programming in R. Getting our code not to make errors is probably a very good first step. But then once your code does an error, you have to go back and make sure that the code is actually correct, right? So it's not going to tell you it's incorrect, but it's so something can be wrong in this model that we fit. And so the way we fix that in here is we say as dot factor. Actually, let me do this as a separate thing. So as dot factor of tumor volume. And now we get the proper coefficient, and it's handling the categorical variable better or properly in our case. And so and this applies for regular linear models as well. When we are working with categorical variables, we essentially get a new column for each category, right? And this is known as dummy encoding or one-hot encoding. And the way I can show you about what's going on under the hood is, okay, so yeah. So the way I can show you what's going on under the hood, R, when we use this formula notation, uses a function called model.matrix. And this is a fancy way of saying that R under the hood understands that, like, when you write MALE, FEMALE, or age group 0-14, under the hood, it's going to have to convert it back into some 0, 1, 2 numeric representation, which is why a lot of data sets come in with a code book, because it's like ready to be statistically analyzed. So under the hood, R will end up converting everything into a number. And let me show you a smaller portion of this. All right, so this is using the head function to quickly look at the first 6 rows of our data set. When we do dummy encoding of a categorical variable, what it's doing is, in this case, tumor volume has 3 groups: group 1, group 2, group 3. What it ends up doing is it turns each one of those groups into a separate column. So the way we read this is, this particular observation has a tumor volume value of 3 because it has 1 for the column of 3. And for this one right here, the ones on the bottom, this particular observation has a tumor volume value of 2 because it has a 1 there and a 0 at 3. And then if it has a 0 for both of them, then it's assumed that that person has a tumor volume of 1. And so that is how every single categorical variable gets encoded in statistical models. And that term that you look for is called dummy variable. It's called a dummy variable, or dummy variable encoding, or the computer science / engineers call this one-hot encoding. Like, I'll put it in chat. It is the number like 1-hot encoding. And so what this does is it takes your categorical variable, breaks it up into n-1 columns, where n is the number of unique values in that category. And it's n-1 because if the value is 0 for both of them, then it's the one that's missing. And there's another reason for that. It's because you're not encoding too much of the same thing in your statistical model. So that's why if you ever hear people like, oh, you need to dummy encode something, this is what they mean. The benefit of using something like GLM in R, using this formula notation, is once you put something as a factor, it does this dummy encoding for you. So you don't have to do it in terms of your own pre-processing step. But sometimes some R stats functions, because it's written by different people, might need you to give it a like this data set directly that's already dummy encoded. And so that is the terminology you need to look for. Okay, so we have this mod 3, and then we can use the broom package to look at tidy to get just the coefficient table. And then what we want to do here is then mutate odds is equal to the exp of estimate. And now we can interpret these things as odds ratios. So because this is the categorical variable, so how do we interpret categorical variables in this case? The way we interpret this, so I'll say the entire statement, is the odds of so the way we can interpret this is the odds of earlier biochemical reoccurrence of prostate cancer after prostatectomy increases by 22.6 times when the patient has a tumor volume of excessive, which is 3, compared to when it is low, which is 1, assuming all else is equal. Right? So when we start interpreting any type of these linear models, it's also assuming all else is equal as if we're trying to interpret a single number. So how do we, if we get a brand new data set in, so for example, we have our, we can collect a new sample. It has, values for age, p-val, pre-op PSA, and tumor volume. We can actually take that new data set, plug it in, and just like the whole, because we already know these beta values, these betas are these columns of estimate, the x's now represent the new bits of information. So what is the next person that just came into into your clinic? You collect their age, you collect their tumor volume, you collect their pre-op PSA values, et cetera, et cetera. You literally plug it in, like fill in these numbers, add in the intercept, and then you get your y. And then if you take the value that you get for y and exponentiate it, you now have the odds of that person, which is, think of it as the probability of that person getting a cancer reoccurrence. And so that's how you interpret and use these models. Okay, so I'll put this last bit in chat for time's sake. At the end of this, actually, I forgot to tell you, we want to now be able to tie this back and how we can plot this. So we can say mod 3 is going to be, I'll just call this betas. How do we go about in plotting these values? So we have to load up ggplot. And remember, ggplot, we're taking the betas data set. Oops. Betas. And what do we want to aesthetically map? Well, we want to map the x-axis is going to be the term, the y-axis is going to be odds, and then what actual figure or plot do we want to draw? The easiest one I can think of right now is point for a, ODDS, if I spell it correctly, point for a little scatter plot-like figure. One thing that you can do, or one trick that you can do, is if your x-axis overlaps one another, the simplest way to fix it is to use this chord underscore flip that will, sorry, not fixed, flip, that literally swaps the x and y axes. And so now we have a nice little plot because we were able to tidy up our model inputs, our model outputs. ggplot understands how to deal with these tidy data frame objects. And so now we can say, hey, plot these two things, and now we can very quickly see, like, this tumor factor is very pro getting you a cancer reoccurrence. And the other way we interpret these values is anything that's super close to zero, that's away from 1 is preventative. And so it seems like age is, if I'm interpreting this correctly, oh no, sorry, I'm looking at the wrong column. All of these values, because of the odds is greater than 1, all contribute to you being having a higher chance of a cancer reoccurrence. Because none of them is less than 1, none of these variables seem to be like preventative. And so that's how we can look at our model that we fit and then sort of tie it back into ggplot, because again, at the same time, it's not very useful looking at these odds ratios in a table, and it's much better if you look at them in a figure. And then you can you can Google and look up other ways of dealing with statistical outputs in terms of viewing them. This is just a very quick way of looking at just the point estimate, which is just the number, and not looking at the confidence interval. Okay, so that's everything I want to go over for today. If we go into the last chapter of logistic regression, there is like a final exercise that you can go through. And so it uses the cytomegalovirus data set that you can load up, and it walks you through fitting another data set and plotting it as a model output. But with that, hopefully this was a light introduction into the world of R. Hopefully you were here because you were interested in learning about R, but didn't really have a sequence or a way to get into it. So I'm really hoping that this was beneficial and helped ease the way of learning and working with R as a data analytics language. For additional resources, and I mentioned this on Tuesday, there is the freely available R4DS book. There is also a community put together resource called the Big Book of R that has every other free R resource essentially listed in one go. There is the R4DS Slack community, and you can join there and there are literally like weekly office hours. So if you are stuck with an R problem, there will be someone there to help you go through it. I'm part of that community, and I'm doing one of their weekly book club readings right now. And the book that they are currently going through is the Tidy Models with R that's written by Max Kuhn. He works at RStudio and works on all of the tidy way of fitting models. And so they are weekly going through a book club reading through that right now. Tidy Tuesday is a community started off by Thomas Mock, and who is I think he's part of customer success at RStudio, and he publishes a data set every week on Tuesday, and people on Twitter using the hashtag TidyTuesday essentially submit their figures from that data set, and I think the deadline is like every Friday. And if you are interested in participating, it is a great way to actually do work with a data set, because finding teachable data sets is pretty hard to find. So this is a great way to just have a data set and just tinker with it. David Robinson streams his Tidy Tuesday stuff every week. So if you just want to, have someone much better than me at R just walk like very quickly, just see how an expert like manages all of these tidyverse tools, you can just watch him go through it, and maybe you'll pick up another function or see how another function is used. For those of you that identify as a lady, there is the R Ladies Slack community group. So if you are intimidated or just another resource for asking people for R help, that is a great way to find out who also in your area are use R. Peter Higgins is with us this round, which is actually pretty awesome. He runs the R Medicine conference, which is under the Linux Foundation, and that happens at the end of August / early September. That is what it has been historically. And so they also have a Slack group that you can join. And there is one more which I will need to look up. I don't know if she's still in here. She's not. But there is a nursing and data science collective Slack group as well. So if you are a registered nurse or work in a school of nursing, there is essentially a Slack group for that as well, which I will ask permission to see if I can post that link up on the slide deck, So if you are a registered nurse or work in a nursing context, just email me and I will let you know. Some of you are at Virginia Tech, and this is also part of my dissertation. So at Virginia Tech, we're part of the data services group, which is part of the university libraries. So you can always contact me or Anne if you're at Virginia Tech to help you with your data problems. This is more like for the Virginia Tech people now, but if you also need help and are at the Virginia Tech location, there is a Center of Biostatistics and Health Data Science that can also help you with your medically related research. For more public resources, and if you're interested in the way I teach and how I learned how to teach, that is all part of the Carpentries, and they also have workshops that they run that you can have at your university to teach you all of the other aspects of computing. And they also have a couple of R and Python resources out that are more general to computing, but some of them are also data focused as well. And last but not least, if you can, please help me graduate by taking the post-workshop survey. That would be really nice. If anything, you can totally skip every single question in the survey. There is one question at the very end, which is really just saying, what did you like how this went? And there should be a section of, given what we've taught today, what would you like to learn next? Because I will also, over the course of this year, be writing the next block of materials. So something that is useful to people in the biomedical field, I will just take your responses from there as a priority to see what else needs to get written. And with that, I will give everyone back the last 4 minutes. And if you have any questions, just let me know. We'll hang around for the next couple of minutes.